Hello. Welcome to everyone joining us from the last discussion and to the people now just tuning into the summit. My name is Billy. I'm the Academy Manager here at One-Click LCA. Now, this session is a little bit different to the others you'll see in the summit. I'm joined by One-Click LCA's training lead, Marius Tsikos, who has been working closely with senior decarbonisation consultants Sarah Bousquet and Rowan Bell-Bentley from ARUP on a new on-demand course on the carbon impacts of mechanical, electrical and plumbing, or MEP, installations, and how these can and should be factored into whole life carbon assessments. In this session, our three experts will provide a brief overview of the topic, answer a few of the most common questions, before Marius walks us through a short practical demonstration taken from the course. But before we start, let me tell you a little bit about us. One-Click LCA empowers the construction industry to decarbonise through its easy-to-use lifecycle assessment and environmental product declaration platform, helping you comply with over 80 national regulations, standards and certifications by providing immediate access to the world's largest LCA database featuring more than 250,000 datasets. The platform is already integrated with the most popular BIM and other industry standard tools to make sustainability calculations a seamless part of your existing workflows. And for over 20 years, One-Click LCA has been making the construction value chain sustainable. You can learn more at oneclicklca.com. For over 75 years, ARUP has been recognised for its vision, talent and tenacity. Dedicated to sustainable development, the firm is a collective of 18,500 designers, advisors and experts working across 140 different countries. Founded to be both humane and excellent, they collaborate with clients and partners using imagination, technology and rigour to shape a better world. ARUP's primary goal is to develop a truly sustainable built environment. This means that in all their work, they aim to identify a balance between the needs of a growing world population and a finite capacity and health of our planet. Now, let me introduce the experts. Of course, we have Senior Lifecycle Assessment Consultant and One-Click LCA Training Lead, Marius Tsikos. Marius, hello.
Hi there. Hi, everyone. Thank you, Billy.
And Sarah and Rowan from ARUP are building decarbonisation engineers with a background in building services. Over the past 4 years, they've specialised in the embodied carbon of building services. Last year, they authored the services chapter of the World Business Council for Sustainable Development report on halving construction emissions today. Thanks to the work they've led and coordinated, ARUP has won the SIBSE 2023 Building Performance Awards in the Embodied Carbon Consultant category. Hello to both of you.
Hi. Morning.
Morning. Now, Marius will take over and kick things off with a short lesson on the foundational concepts of whole life carbon in the built environment and life cycle assessments.
Thank you, Billy. Thank you. All right, so before we start, let's do a very quick recap of what is whole life carbon. So whole life carbon is the carbon emissions or carbon equivalent emissions that are occurring throughout the entire life of a building. This includes the raw materials extraction, like limestone, iron ore, and other materials, the transportation of those raw materials to the factories, the manufacturing of construction products using these raw materials, the transportation of the construction products now from the factory to the construction sites, the construction site related emissions themselves. Then we've got the use states, which is where we've got emissions related to the operational energy use, operational water use, but also material replacements and maintenance. And then after 50, 60, 100 years, something like that, we've got the end of life stage. So this is when we deconstruct the building and we have the associated emissions again from the energy that we need to do that. We've got transportation related emissions again, because we need to get these demolition or deconstruction materials from the site to the recycling facilities or the landfills. We've got emissions associated with recycling, when we get steel scrap to the recycling facility and turn it into recycled steel. We've got emissions that are occurring at the landfill once we dispose some of those materials, for example, methane emissions if we dispose organic materials. And of course, after that, we've got Module D, which represents the benefits and impacts beyond the system boundary. So mostly benefits from recycling, reusing, or recovering the energy from incinerating some of those materials. So whole life carbon can be split into embodied and operational carbon. So we already talked about emissions from materials and emissions from energy and water. Embodied carbon is the emissions related to materials, simply put, transportation of, manufacturing of those materials, transportation, replacements, maintenance, and end of life treatment. And then we've got the operational one, which the operational carbon, which is the carbon emissions associated with operational energy and water consumption. This is the energy that we consume as building users, for example, for heating, cooling, and lighting, and fresh water that we consume during the use of our building. In a tidier way, we can see all these life cycle stages and modules here in a table format. Some of you might already be familiar with material-related modules on the top and operation-related modules like energy and water consumption at the bottom. Now, these two modules, the operational ones, B6 and B7, are the ones that make MEP a bit more special when it comes to whole life carbon assessments and optimization. This is because MEP equipment, obviously, it comes with embodied carbon, just like any other product and material, but at the same time, it plays a significant role in operational carbon because it is the equipment that will consume this energy to deliver heating, cooling, lighting, and fresh air in our buildings. This means that it should never be an exercise of just reducing MEP embodied carbon, but really optimizing the whole life carbon for building services. Now let's see how these embodied and operational impacts are spread throughout the building's life. We can see upfront carbon happening at moment zero on the left-hand side of this graph. And this is the embodied carbon from construction products that are initially installed in our new building. And then we've got operational impacts from energy and water use, which we can see are reducing over time for various reasons, including the electricity grid decarbonization and also phasing out of fossil fuel energy sources and improvement of energy efficiency in existing buildings that will happen definitely in the future and these kind of things. And then we've got also replacement impacts and end of life, which are associated to materials. And how does MEP compare to other building parts and systems? In this slide, we can see how a building is split into the various layers like the site, the envelope, the structure, the MEP services, the space plan, and finally all other things that are coming in with the building occupants. And here we can see a sample of 15 projects that were assessed by ARUP and how the embodied carbon impacts are split by building part. We can see that the share of building services typically ranges from 20 to 30% in average. And this means that although it is quite commonly underestimated and left out of scope for building LCAs, it has higher impacts even than the structural frame in many cases, as we can see. Continuing on the assessment scope, let's see what difference it makes in the interpretation of results as well. So on the left-hand side, we see that the share of MEP impacts in an upfront carbon assessment is 18% in average for a sample of 6 case studies in this case. And for the same study with an expanded scope, except B6 and B7, so we're doing an embodied carbon assessment, whole life embodied carbon assessment, this number becomes 32%, while the share of impacts from the structure is being reduced. This is simply because, in an upfront carbon assessment, we're not taking into account impacts from replacements, maintenance of the MEP systems and other systems, which is something that is practically not a thing for the structure of a building, since in most cases it will just stay as is for the entire duration of the building. So that's that about the importance of MEP in whole life carbon. But what must we do and what must the industry do to face this challenge, and what does the industry already do? First of all, addressing the whole life carbon emissions from building services must be part of an overall carbon reduction effort. So we never look separately embodied carbon or separately operational carbon. We need to take a whole life cycle point of view perspective. This starts with operational reduction first, with reducing the energy demand initially by passive design and using the right active technologies, and then maximizing the on-site renewable energy generation. The rest of the operational impacts, which in some cases there will be some, they should eventually become zero via the electricities or the electricity grid decarbonization in the future. On embodied carbon now, we need to look into how to redefine our needs, first of all. So, for example, do we need to build new, or can we refurbish, strengthen, and expand an existing building? Then, what materials and products can we reuse? How can we design our building so that we allow all these materials and products to be reused again in the future? How can we reduce material use overall? How can we reduce on site waste? So, when we actually start building this building, and what manufacturers and products are available, and how do they compare when it comes to embodied carbon. Whole life carbon reduction in new and refurbished buildings is something that the entire industry is looking at the moment, and governments are also setting national targets to become net zero economies by 2050 or something like that, as we can see in this slide. Progress might not be as good as needed, for sure, but these commitments definitely show the way that we are going, or we should be going, and the way that our industry must take as soon as possible. Several countries are already taking measures to decarbonize their construction industry. In Europe, countries like Denmark, Sweden, Norway, Finland, and France, they already have whole life carbon requirements in their building regulations, while recently in the EU, at an EU level, the new EPBD directive that mandates all EU countries to have such requirements by 2027, it just became an actual law. So this will happen everywhere in the European Union within the next 3 years. Outside Europe, there's also a lot of movement, with California probably being the best example, which recently introduced such requirements in its building codes called Cal Green. So these regulations are creating an extra driver for clients to reduce emissions, as they will need to obviously comply with the regulations, but most clients nowadays set up their own commitments as well that are often more challenging than what regulations require, which is great. This is done as part of their own social responsibility commitments in order to get access to green financing, and of course in order to achieve their own sustainability commitments. For those clients that do not necessarily have their own goals yet, when it comes to net zero carbon, certification schemes are the main business driver. These are multiple schemes from across the world that award more and more credits or points for undertaking a whole life carbon assessment or a life cycle assessment, and actually reducing the embodied carbon of the building. And in this slide, we're just mentioning a few of them, like BREEAM, LEED, and Green Star, but there are many others from across the world, really. And then there are also voluntary initiatives like the MEP 2040, where MEP engineers participating commit to reduce carbon emissions from MEP systems. We've got the Built Environment Declares movement and several others, really. So it looks like that our industry must be transformed in order to achieve this net zero goal that we and our countries and governments have set up. But how are we going to achieve this if we don't have the right skills? In a recent report conducted by LinkedIn on the green skills gap, we can see that the demand for green skills is almost double of the supply. This means that one of the first things that we need to do as an industry is to upskill ourselves with green skills. And this is why we have created our academy, our own academy at One Click LCA. This is how we are trying to educate the construction industry in anything LCA and embodied carbon related. And we do this completely free for our students. And we do this with reputable partners like ARUP in this case. Today, I'm very happy to announce the publication of an on-demand course that we developed with ARUP about whole life carbon optimization and tailored for MEP engineers. You can find and enroll to this new course by scanning this QR code in your screen, or by just visiting academy.oneclicklca.com. And with that, I will hand it over now to Sarah and Rowan to tell us a few words about the contents of this course and give us an idea of what students will learn by taking this course. Thank you very much. Sarah and Rowan, over to you.
Thank you. Thanks, Maris. Sarah and I are now just going to give a quick overview of the course and share some of the highlights. The course is designed for building service engineers and sustainability professionals. It begins with an introduction to the environmental and sustainability issues associated with buildings and MEP designs, as well as some of the drivers for change, which Maris has kind of already touched on. It then introduces key LCA concepts and data sources, along with design opportunities to consider to reduce whole life carbon in MEP. And these are demonstrated throughout the course using real project examples from our work at ARUP. And then the final section of the course takes you through how to carry out an LCA for MEP, how to set up a project, how to collect design data and carbon information, and how to review and interpret results to optimize the performance. So the course aims to empower people to use whole life carbon assessments to reduce the impact of MEP designs. This diagram is a lot of information on, so it is in the course and you can kind of study it in more detail there. But the diagram kind of shows how we should use them to do this all the way from brief definition to operation of the building. And as well as ensuring we're carrying out assessments throughout the life of the building, we need to make sure that there's this feedback loop to help improve the accuracy at early stages, so we can make informed design decisions more quickly. It's essential that whole life carbon assessments are utilized to reduce whole life carbon emissions and not just carried out as a kind of tick box exercise or simply to comply with regulations.
And in the second chapter of the course, we dive into LCA concepts and data. So there are a range of standards and frameworks to assess the whole life carbon of buildings, such as the RICS professional statement in the UK or the Levels framework in Europe. And to calculate embodied carbon, these rely on EPDs, environmental product declarations, or PEPs, product environmental profiles, which provide detailed information about a product's environmental impact. But these documents can be challenging to create for MEP equipment because of the wide range of products and applications and the complexity of the supply chains. So in order to fill the gaps in MEP products data across the industry, CIBSE published the TM65 methodology in 2021, and its objective is to help manufacturers, MEP engineers, and LCA consultants estimate embodied carbon of products while EPDs or PEPs are under development. And in the course, we tell you a bit more about this methodology, which relies on information provided by the manufacturer about a product's material breakdown and, if it's available, the energy that's used in manufacturing. And depending on the level of information available, there are two levels of calculation possible, the basic level and the mid-level calculation. The basic level method uses the material breakdown and material carbon factors to estimate stage A1, followed by some assumptions about the repairs, and then the estimated emissions are scaled up based on the complexity of the product to account for the remaining stages. The mid-level calculation method uses the material breakdown and material carbon factors, as well as energy used in manufacturing that's provided by the manufacturer. It also provides assumptions about transport distances and the types of transport, repairs, and end-of-life scenarios. And then for both methodologies, a buffer factor of 30% is applied to provide an adjustment for the simplicity of the approach, and the leakage from refrigerant is captured in stages B1 and C1, and that's calculated separately. So this methodology is really useful to engage with manufacturers who haven't yet thought about embodied carbon, so they can start to gather information about their products and supply chains. But TM65 should not replace EPDs or PEPs, which provide more detailed and robust information and which are independently verified.
So the third chapter of the course looks at ways in which we can reduce the whole life carbon of MEP. So on a project, it's important to think about carbon at the early stages, not just when we get to the detailed design stages. On the screen are some key questions to ask at the start of a project that can help you to do this. So one of the main things we need to do is to challenge and influence the brief in order to reduce the size or extent of MEP systems. For example, if we were to look at kind of broadening the temperature band within the space to allow for adaptive comfort, then we can reduce the operational emissions from the heating and cooling systems, as they won't need to run for as long throughout the year. And we can also reduce the embodied carbon by reducing the required capacity or size of the plant associated with these systems. As we start to develop the design, whole life carbon can and should be used as the metric to assess the options. So the earlier in a project we start to consider the whole life carbon, the greater the opportunity we have to reduce it. Although information may be limited at these early stages, we must estimate whole life carbon emissions to guide the decision making before design choices are locked in. And one of the most impactful ways we can do this is to carry out whole life carbon optioneering. So the diagram on screen shows the process for carrying out a whole life carbon optioneering study. So you're looking at the operational and embodied and then kind of bringing it together to look at what is the best overall. So similar to the use of CapEx and OpEx to see if a design will pay back financially, we can use embodied and operational carbon to determine which option will yield the biggest carbon saving. When carrying out these studies, it's also important to include sensitivity analysis to help to address the uncertainty within these estimates and identify any tipping points, as well as identifying the most critical parameters that are affecting the whole life carbon emissions. So whole life carbon optioneering is particularly important for building services systems, as there can be a tension between operational and embodied carbon, both of which are the responsibility of the building services engineers. Certain interventions have the potential to reduce operational carbon at the cost of increasing the embodied carbon. So for these types of measures, optioneering can help us to find that balance point and make sure we aren't spending more embodied carbon than we're saving operationally, therefore minimizing the whole life carbon emissions. The example on screen demonstrates this concept using the example of insulation, where additional insulation reduces the operational carbon from heating systems, but increases the embodied carbon of the facade. So in the course, we look at ways to reduce the operational energy and water associated with MEP systems, as well as how to reduce the embodied carbon of central plant, on-floor equipment, and distribution systems. But now I'm just going to talk about distribution. So on screen are the results from an ARUP study of 6 commercial buildings based on stage 4 design information. The study showed between 25 to 70 kilograms of A1 to A5 embodied carbon per meter squared was associated with MEP distribution systems, and cabling was excluded as this was not modeled as part of the stage 4 design. So the values will vary for different servicing strategies or building types, and they shouldn't be used as benchmarks, but they demonstrate the relative impact of different distribution systems within commercial buildings. So the system with the largest embodied carbon impact was ductwork and its associated insulation, accounting for 58%. And even without cabling, the cable trays, basket trunking, and ladders made up 21%. So what can we do to reduce the impact of distribution? The first thing we should consider is removing the need for distribution systems altogether. For example, you could consider instantaneous hot water heaters to remove the need for domestic hot water pipework. If the system can't be removed, we should reuse as much as possible within existing buildings or source distribution from other sites using marketplaces such as GlobeChain. We can optimize distribution routes to reduce material use and consider centralized and decentralized options for a system to see if the reduction in distribution associated with a decentralized option outweighs the potential embodied carbon uplift due to increased equipment quantities. And when options to remove, reuse, and reduce distribution quantities have been explored, you can look at using lower carbon materials, specifying recycled content, and prioritizing products with embodied carbon information. And finally, we can design for deconstruction to enable reuse at the end of life. And some of those key principles for building services are shown on the right-hand side of the screen. But how do we ensure that a low carbon design results in a low carbon building? We need to embed requirements into specifications so that all actors in the chain are kind of working towards the same end goal. We must set project operational and embodied carbon targets at building and discipline level. And we should also request environmental product declarations or EPDs in project specifications for MEP systems. And we can set a target for the percentage of products installed with EPDs. And finally, we can include carbon performance requirements in specifications as well. For example, we could include refrigerant global warming potential or GWP limits.
And in Chapter 4, we go through this LCA workflow in more detail. The first step is to define the brief and the purpose of the assessment. The next step is to gather information about the building services systems in the building, then to carry out the assessment using carbon data and tools like One-Click LCA. Then the next step is to review the assessment, the assumptions made, and the quality of the data used before interpreting the results, presenting them, and working with the wider team to optimize performance and reduce whole life carbon emissions. So I'll just share with you a few highlights from this chapter. On gathering project information, the availability of information varies significantly depending on the design stage that the project is at. So at concept design, estimates can be made using rules of thumb and previous projects. Then more detailed calculations, modeling, and actual equipment specifications can be used at detailed design. At construction, as-built information on the quantities and the types of products and distribution installed can be used. And when the building is operational, metered data can be used to feed into a lifecycle assessment. Once the LCA has been carried out, it's important to present the results clearly and to communicate the limitations of the assessment, particularly for building services. So think about completeness, what is and isn't accounted for, the scope of the assessment, are the whole life carbon stages that were considered clearly indicated, because results for A1 to A5 and A to C will be very different. Have any benchmarks been used? In terms of decarbonization, what trajectories have been selected for operational carbon? And about data quality, was the data used specific to the equipment specified? What sources of data were used? And have you reported a carbon data uncertainty factor, which can follow guidance from the latest RICS professional statement? So these are some of the steps to go through when analyzing the results of an LCA in order to identify reduction opportunities throughout the design and construction. So if an LCA has been done for the project at a previous stage of design, then comparing the results with previous assessments is really important to identify and communicate the impact of changes with the wider team. You could also compare the results of the LCA with industry benchmarks. And then you should look at the results in more detail, split by subsystem, to help you identify some of the hotspots and which systems are most carbon intensive. And the next step is to collaborate with the design team, with the client and the contractor to identify reduction opportunities that are based on the hotspots identified. And the last step, often easier said than done, is to implement these changes throughout the design and construction in order to reduce whole life carbon emissions. We also share a few case studies to show how results can be displayed. So this is an example from an optioneering analysis done for an educational building on the ventilation strategy. The study looked at the impact of centralized versus decentralized ventilation on the whole mechanical design. And there you can see that the air handling units, the ductwork, and the air source heat pumps were the biggest contributors to embodied carbon. Option 3, with a centralized system, was most intensive, and the embodied carbon from the additional ductwork wasn't offset by the removal of the MVHR units. So this helped the team choose a decentralized strategy for ventilation. For the same project, the team assessed the embodied carbon of all MEP systems in the building at stage 3. This showed what some of the hotspots were for the project, ductwork, refrigerants, and lifts, and this insight was used by the design team to further optimize the MEP systems. There you can see again that reporting the results for A1 to A5 and A to C separately helps to visualize the impact of the replacement cycles and the refrigerant. So we need to report results from LCAs with enough granularity to guide reductions in whole life carbon, so that we meet ambitious targets at individual project level, but also at the industry level, so that we're meeting the decarbonization objectives for the construction industry. So I'll hand you back to Marius for a quick practical demonstration, which is taken from our upcoming course.
Thank you, Sarah. So in this demo, you will see just one of the videos that we have included in the course. In this case, we are showcasing our new LCA tool for MEP engineers and how one can basically model the billing services of, in this case, a data center billing using one-click LCA assemblies at an early design stage. As I said, this is just a snippet, so we've got lots of other videos and a lot of different material. And the whole course goes into more detail, both in terms of theory, but also in terms of software demonstration. So yeah, there we go. Hi, in this session, we will go through the embodied carbon modeling for MEP equipment. We will do it in two different ways. We will start with modeling in detail first, all the different pieces of equipment one by one, and then we will also see how we can model the MEP embodied carbon using one-click LCA assemblies at an early design stage. So starting with the detailed version of it first. We are going to start adding some equipment. I am using the MEP tool right now, which is tailored for MEP engineers. You can still model the MEP impacts in many other tools, but this is tailored for MEP engineers. It has a reduced scope, so you can focus on MEP equipment only, and it is easier to find what you really need to include in your assessment. So let's start with HVAC system. We're going to add some ventilation. First, some duct, probably. So let's go with any of those. Really, it doesn't make any difference for this case. I'm going to add that one. And let's say we've got some 100 kilos of this material, which is going to be used for steel duct work. Then we can also add some insulation. Let's go with any of those, glass wool insulation for pipes, assuming it's going to be the same for ductwork as well. So let's go with that. Let's assume that we've got another 100 meters of that. We can always change the unit to a different one from the available ones. Then finally, just let's add some air handling unit. There's going to be a lot of more materials, but let's just do this for these three. HVAC components and equipment, that's going to be somewhere there. And let's add this one. Should be good. And let's assume that we need like a couple of pieces like this. In real life, in order to represent the exact equipment or the exact size of equipment that you'll need in your project, you will need to compare the size of that equipment with the size of the data points. So if you need 2000 cubic meters per hour of air exchange, then you need to add 2 of those data points in order to represent the size of that equipment that you will specify. So that's that. We're going to save. And we will get a preview of the embodied carbon right here in absolute values, but also as a percentage share. All other impacts are being calculated automatically. So we've got the transportation impacts that depend on the transportation distance and the mode of transport. We've got the replacements. So this means that this will be replaced at least once if your service life is 60 years. This and this one will not be replaced unless you change the service life. And then we've got the wastage, which will contribute to A5 impacts, and then the end-of-life impacts, which contributes to end-of-life states like C1 to C4 and module D. So that was a detailed version. I'm going to remove those now. And let's assume that we are at an early design stage. We don't have much information. We know about the types of systems that will be added, but we don't know the exact material quantities. Let's assume that we're modeling the MEP equipment for a data center. So let's start adding some assemblies. So assemblies in one click LCA are basically groups of materials that represent an entire element or a component. In the case of MEP, this can be an entire system, really. For example, the HVAC system for data centers. We don't need to add all these different materials one by one like we just did. We can add an assembly, and this will take into account the air handling unit, the ductwork, the insulation, the pipes, and any other material that goes into that. We can add a second assembly for electrification, another one for fresh water, another one for wastewater, and so on. So let's try to build the entire MEP equipment of a data center now using assemblies. Let's go with HVAC system. There we are, HVAC system for data centers. Let's assume that our building is going to be some 5,000 square meters. So now we're trying to replicate all the MEP equipment and the associated materials for a 5,000 square meter data center. Then let's add some cabling. So we will look for electrification system. Let's go with that. We can always check the background information. This is obviously a one-click LCA assembly, so there's always going to be some kind of description of what it represents or where it is based. Let's add this to our model. And that's also going to be 5,000 square meters. We can now add the fresh water. There we are. And let's add another 5,000 square meters here. And finally, let's add waste water as well. Let's go with constructions. We can go with that. Wastewater and rainwater, and add another 5,000 square meters. So these 4 different assemblies, they represent different 4 different systems in this building type. If we click at the plus icon here, we can see that it expands, so we can see all the different materials that this assembly is made of. If we change the original quantity to anything like, let's go with 10,000, we can see that it changes the material quantities as well. Let's make this back to 5,000, and the same goes for everything else. So the benefit in this case is that you don't need to calculate on your own all these different materials. You don't need to have your own benchmarks, like how much ductwork is needed per square meter for this building type, or how much pipe work is needed for this building type, and so on. So these benchmarks are already there. You can go use the assemblies and get your baseline LCA results, and then it should be a matter of trying to reduce these impacts. So finding ways to make the distribution routes more efficient, or using different materials, or using different products, and so on. So I'm going to save this now, and this will
update the results, the preview of the results in the building materials tab.
All right, that concludes the video demonstration of one-click LCA and the new LCA tool for MEP engineers. To close this up today, I'm going to address some of the most commonly asked questions regarding to MEP LCA to Rowan and Sarah. And first one is if you can let us know what are the most common challenges you currently face when you calculate MEP whole life carbon in your day-to-day work.
Yeah, I think one of the biggest challenges that we have faced is just making sure that we have 100% coverage of MEP systems, because there are so many different systems with so many different parts to them, which can be designed by multiple different designers. It's really hard to make sure we are covering everything. And then there's some systems like the cabling, for example. When I showed the distribution study, we actually don't model the cabling at stage 4 even. We only really know the quantities of that when we get to site. So I think, it's really challenging to make sure we're covering everything and like including allowances for those things that we don't yet have the data for. Yeah, so as well as trying to get 100% coverage, as Sarah mentioned in the presentation, it has been quite hard in the past to get embodied carbon data for some building services systems or pieces of equipment. We are starting to see more EPDs being produced, particularly with the regulations coming into force in Europe. And CIP-CTM 65 does go a long way to kind of filling some of those data gaps in the meantime. But we still need to see this kind of improvement in data in the industry as well.
And just to add to that, there's also a lot of uncertainty around in-use emissions in the buildings. So we've got uncertainty around maintenance and replacement activities. We can use standard service lives for products, but we know that this varies quite significantly depending on the maintenance regime. And in terms of operational carbon, there is still an operational performance gap. So if we rely on energy modeling data to estimate embodied operational carbon, then we risk the results being skewed by that performance gap. And we also don't have a very good understanding of the real refrigerant leakage scenarios in buildings, so we rely on a limited set of data to estimate this and guidance from CIP-CTM 65. And then finally, there's some more uncertainty around future decarbonization trajectories, which affect both operational and embodied carbon. So loads of challenges, but these shouldn't stop us from measuring and reducing whole life carbon.
Thank you very much. Next question. Cross-discipline decisions are key to enable low carbon design, particularly at early design stages. So do you have any examples from your day-to-day work to give us?
Yeah, definitely lots. So I have a mechanical engineering background. So one of the key things that comes up is, which we kind of touched on in the presentation, optimizing the facade. So at the start of every new build project, there's a debate of how far do you go on increasing the performance of that facade to reduce the heating and cooling loads of the building. Or if it's a retrofit as well. We've had a lot of debates. Should we be replacing the facade? It's adding so much embodied carbon, but it is obviously going to reduce the operational carbon from those heating and cooling systems in the building. And the results of studies that we have done on the projects, have come out kind of different each time, depending on the type of the project. If it's a retained facade, how well is it performing at the moment? It's really important that pretty much everyone across the design team, the architects, structural engineers, facade specialists, and the mechanical engineers all kind of work together to assess the whole life carbon impacts of this option.
Yeah, my background is in public health engineering, so I can share an example about coordination with the structural team on the basement, particularly with all these huge tanks that we usually put in buildings, particularly for sprinkler protection. So for a mixed-use building, and we've got this case study in the course, the design team kind of looked at different options of tank material, so either glass reinforced plastic or concrete tank for the sprinkler storage. And although the glass reinforced plastic has a lower embodied carbon as a material than concrete, it's got less flexibility than concrete in terms of the shape and the height of the tank that we can achieve. So for this particular case study, using a concrete tank meant that the basement size could be smaller, and so the overall embodied carbon of that solution was lower than if we had a GRP tank.
Great. Thank you very much. Another question, third one. We already discussed about the benefits of assessing whole life carbon or estimating whole life carbon at early design stages. We can see the benefits. But what value does measuring whole life carbon add at later design stages and during construction when the team has, admittedly, they have less opportunity to reduce the building's impacts?
Yeah, I mean, I think it comes back to the kind of data issue that we talked about. It's only really in recent years that we've started to do these detailed whole life carbon assessments of building services. So even though we're starting to do them more often, we still don't have that much data about the actual quantities that are getting put into buildings on the embodied carbon side. And obviously, Sarah touched on the operational performance gap as well. So I think it's really important to get this actual construction data to kind of help feedback to make those early stage decisions before we are kind of locking that carbon in with those big decisions. The more data we have that can feedback and help with that, the better.
And this can contribute to more robust and more transparent industry benchmarks that help us assess the performance of buildings of different types, and kind of understand trends, how a building compares with others, what we need to do collectively to get to our decarbonisation objectives. Of reducing embodied carbon by 40% by 2030. That's one of the UN breakthrough goals. That's a big reduction. If we're not sharing data collectively and not sharing lessons learned, it's going to be very difficult to get to that objective.
All right. Thank you very much, Rowan and Sarah. And then final question for you. What are the key takeaways for the students from this course?
So I think one of the first takeaways is that historically building services engineers have focused on operational carbon and improving energy efficiency of buildings, but the embodied carbon of MEP is also really significant and we can't ignore it. The second one is that we think MEP, whole life carbon analysis and optioneering needs to become business as usual, particularly at early stages on some of the key cross-discipline decisions, so that this can guide decision making and help us meet the reductions that the climate science requires.
Yeah, and I think the final point is all around data. We need to collaborate across the value chain to increase the carbon data available and ensure assessments are as accurate as possible. And data collection and sharing is going to be essential to fill those data gaps across the industry and build better benchmarks. Measuring carbon needs to help us to reduce it, essentially. We need to be sharing this information and making better decisions as an industry.
I think that's a great point to end there. Thank you very much, Sarah, Rowan, and Marius.
Thank you very much for having us. It's been a real pleasure to develop the course together and then to talk about MEP whole life carbon with you today.
So what was supposed to add to that, Sarah? It was very comprehensive.
I think that pretty much covers it. Marius and I have had a really good time working together on the course, and yeah, excited to share it with everyone. But yeah, thank you to everyone who's tuned into this session. If you'd like to read a little bit more about ARUP, you can head to this QR code here. And then if you'd like to find out more about One Click LCA Academy training courses, these are delivered for free as part of our commitment to train 1 million low carbon experts by 2030. Attend one of our live week-long boot camps for a comprehensive training on EPD and LCA concepts from our in-house experts. Enroll for the next one via this QR code on the slide or by visiting academy.oneclicklca.com. So if you'd like to book a demo and get advice on decarbonising, just click yes in the poll that you can see in the Livestorm environment. Finally, we are always happy to hear from you. If you would like to contact OneClick LCA, please visit oneclicklca.com, or to learn more about our construction and manufacturing LCA software, write us directly via sales@oneclicklca.com. You're also welcome to follow us on LinkedIn, check out our new YouTube channel. There's rich content there about decarbonising the industry. But yes, thank you all for now, and see you next time. Goodbye.